Okay, any questions about the capacitors? Now we will be changing the subject. We will be starting to study the currents. Before we start the currents, any questions about capacitors? Yes. Now we are beginning to study the motion of charges. The charges will no longer be at rest. But still electrostatics will be kind of a the first approximation to this phenomena. Now we will be combining kind of the electrostatics that we have learned plus some Newton's laws, and we will see how the charges are moving in a conductor. Now let's see, we have already studied this capacitor. We know that we can charge this capacitor, positively charged and negatively charged. Now we already know that in a conductor, inside the conductor, we have the same potential. There is no potential difference. Now if you look at this part, we know that this, let's say, if one of the charges, if this is at, let's say, this is V equal to 0, we can just choose that negative plate to be at V equal to 0. Then this positive plate will be at the potential V. Now, I don't need to specify any point on these plates because we already know that since the plates are conductors, every point has the same potential. Now, what happens if we connect these two? Now, we have this plate, which is a conductor, which was at the potential V at all the points. This plate, which was a conductor, which we said that it also has the potential 0 at every point. Now we connect both of them with the same, with another conductor. Now all of these points are on the same conductor, but we have a potential difference. So what happens? It's not. It will be. The charges will be moving around. Now, we also had seen the same example when we were saying that, okay, when we argued that in a conductor there cannot be an electric field. If you remember our discussions, let's say this is our conductor. And we just imagine, for example, putting some positive charge near our conductor. Now, in the absence of this conductor, we already know that the electric field lines will be straight. This is electric field lines. So without a conductor, we have electric field lines passing through, let's say, this point. Now, what happens to that electric field line when we bring the conductor? So why does it disappear? Where does it go? Any ideas? What happens to this electric field over here when we put the conductor over there? No. The conductor gets polarized. Remember, if there's electric field, it will exert a force on the charges. Now, what we call conductor, or any matter in fact, is just a collection of positive and negative charges. The difference between a conductor and an insulator is that in a conductor, there are some charges that are free to move around. In an insulator, all the charges are fixed. They cannot move around. Or you can also think of, in a conductor, the positive and negative charges can move relative to each other, but in an insulator, they cannot. For example, pure water is not so bad an insulator, because although the molecules making the water, they are free to move around, both positive and negative charges, they move together, so you cannot separate the charges. In a conductor, if you put some salt, which is nothing but the positive and negative ions, the ions will be free to move around, so it will be a good conductor. And if you just connect water to a battery. Have you tried it? Just take a battery, prepare some salt solution, connect the two ends of the, connect the battery to a wire and put the wire in the water. No? Nobody tried it? Okay, so you'll see these bubbles. You can collect those bubbles and get some nice firework. So here we have a conductor. We put it in a conductor, meaning the charges are free to move. Let's just say it is a metal. A metal just means the electrons are free to move, not the nuclei. They are heavy. They will be fixed at their position, but the electrons will be free to move. So when I put the conductor in this electric field, the electrons will feel a force in the opposite direction to the electric field. And so I will have negative charges, let's say electrons, will accelerate in this direction. So I will have less electrons in this region, more electrons in this region. It will create some additional electric field, which will cancel the electric field inside the conductor. The total electric field will be 0. At this point inside, at any point inside the conductor, I will have an electric field due to this external point charge, plus another electric field due to the separated charges inside my conductor. The sum of these two electric fields will be 0 when I reach electrostatic equilibrium. Because as I wait here, there will be more and more electrons moving towards this side. So the surface charge densities at these two opposite surfaces will increase, and hence this additional electric field will get stronger with time, and eventually the electric field created by the motion of these electrons will be strong enough to cancel the electric field created by this external field, and we have 0 electric field. 0 electric field, 0 net electric field inside our conductor. Now the question is, what happens if you see the electrons will be moving in this direction, but somehow you take those electrons away and put them on the other side? So no way there won't be any accumulation of electrons in this region, but that means the electrons will keep moving in that direction. And that's what we call basically a circuit. Now the device that we use to just pick up the electrons from this surface and dump them on the other side is what we call a battery. So let's say, okay, we have this, let's say metal. We take a battery. This is the positive and this is the negative. And so what the battery does is that it just takes electrons from this positive terminal and gives away electrons. Of course, at a higher energy, lower potential. Well, that is basically the battery. It creates some potential, but it basically maintains a potential difference between the two terminals by just taking electrons from the positive terminal and giving away electrons from the negative terminal. And we say that, okay, since the electrons are moving in this direction, you can imagine it as positive charges moving in the opposite direction. So this is the direction of the current, the conventional direction of the current. So this is the basic idea of the current. Now, what happens inside? So the battery, by just giving away electrons, you can just imagine it as a kind of a parallel plate capacitor. So that you will have some negative charges accumulated over there. Well, since you are taking away electrons from the other plate, you will have positive charges. And electrostatic equilibrium is never reached. Now, we do reach a stationary state where nothing changes, nothing apparent changes, but the charges are constantly moving from one direction to the other direction. Now, there is an electric field created inside. Now, this electric field is not 0 anymore. And before we said that, okay, inside the conductor we cannot have an electric field. Now in this case we have an electric field inside the conductor. In fact, we have to have an electric field inside the conductor. Because the difference of this case from the previous cases when we said that there cannot be an electric field is that before we said that we reach electrostatic equilibrium. When we reach electrostatic equilibrium, we had no electric field in a conductor. But in this case, the battery, this battery that we connect over here, prevents us from reaching electrostatic equilibrium by constantly taking the charges from one place and putting it on the other place. So if you just imagine one electron here, so what is the direction of the force that the electron will feel? Towards the left, towards the right? Since it's negatively charged, it will feel a force in the opposite direction to the electric field, so it will feel a force towards the left. This is the force that the electron will feel. Now, if the electron is feeling some force, it should accelerate. So that's what Newton tells us, that the electron is a mass. It has a mass. So we are exerting a force on it, so it should have an acceleration. Now the problem here is that the electron is not moving in vacuum. There are all kinds of other nuclei, other electrons around. So if you just, let's say this is our electric field, this is the direction of the electric field, this is our electron. Now the electron in any material is in fact constantly moving. If you imagine the atom, the electrons, you can just imagine as if they are just rotating around the nucleus. They have a huge velocity. Well, in a conductor, some of the electrons at least, they are not bound to the nucleus. They just move around in the conductor. So as they move around, they will just hit other electrons or other nuclei. So in the absence of the electric field, so let me just divide this into two. So in the absence of the electric field, if you imagine a single electron, it will, at some instant, it will be moving in one direction, then it will hit something over there, and it will bounce back. It will just bounce back and forth. Yeah. But you see, on the average, it will just stay where it is. It will not move. I mean, it's just like, if you just imagine let's say a bowling ball inside this room, you just throw it fast, it will just hit the walls, and it will just stay here. It will not go anywhere. But if you apply an electric field, this is our electron, we have this electric field, it will be accelerating. It will accelerate and then hit something, transfer its energy, but nevertheless it will just bounce back. It will just scatter around. But you see, since it feels a force in that direction, its trajectories are always bent. It feels a constant force. And the motion in a constant force field is just a parabola. Depending on where it scatters after the collision, it might move towards the left, towards the right, but nevertheless it will just, the trajectory will always, between two collisions, it will always bend in the opposite direction of the electric field. Now this bending will just cause the average position. Remember, we started from here, and then the electron, after many collisions, is now here. Now we have what's called the drift velocity. Its velocity between collisions is huge, comparable to the speed of light. If we exert an electric field, it will create a tendency for the electron to move in the opposite direction of the electric field. So it will acquire some velocity in the opposite direction. Now, the velocity in this case, the speed, the drift speed, so to speak, turns out to be proportional to the electric field, the magnitude. Now you see the force is proportional to the electric field, and the force is proportional to the acceleration. It should be the acceleration proportional to the electric field But rather than the acceleration in this case, since we're just doing this random motion back and forth, the drift velocity itself turns out to be proportional to the electric field. You can just imagine this as a kind of a terminal velocity. Now, if you remember when we were discussing the terminal velocity in mechanics, we said that there is a force proportional to the velocity. So if the velocity is too fast, it just cancels its weight, so the velocity will just remain to be constant. More or less the same thing happens over here. As the drift velocity turns out to be the terminal velocity turns out to be the proportional to the electric field. And by the way, this drift velocity, if you just estimate it, it is around 0.02 millimeters per second. This is an estimate in your book. This is small. Nothing to do with the speed of light. It is moving with the speed of light between collisions, but after its collision, it has a more or less equal probability to scatter in the opposite direction of the electric field as well as in the direction of the electric field. But now there's another question. If this drift velocity is so small, how is it that when okay. So how is it that the moment that I press this button, the lights go off? Doesn't go off? Yes. No. So it's almost instantaneous. I mean, definitely the electrons with such a drift velocity, they're not going over there. They're not reaching over there. So how come that the moment I press this button, the lights go off and they come back on almost instantaneously? I mean, if you just imagine the distance is typically of the order of 10 meters, let's say. If you have 10 meters, well, it's 10,000 millimeters, 10 to the power 4, divide by 6, 10 to the power 6 seconds, that's hours. It will take an electron that leaves this switch to reach the other end of the light bulb over there, hours to reach. Yes? So who wants to do an experiment? For example, the fourth row over there is quite crowded, right? So if your friend on this end of that row pushes the friend next to it, how long does it take the message to go to the other end? It will still take a long time. They're not replacing each other. Okay, that's a question for you to think about. I will not answer it. I will not keep discussing it. Think about it. I will not discuss this question. So that is something you have to keep in mind. I mean, while you are listening to these lectures, that should be one question whose answer you should be looking for. You will, don't worry. Okay, so this is the drift velocity of the electron. Now, if you imagine, this is my metals. I am exerting an electric field, creating an electric field due to the battery, and I will just ignore the drift velocities. I will just study the drift velocity. I will ignore the instantaneous velocities of the electrons. So if I imagine the drift velocities, the electrons here, they are moving. They will be all in motion. So if I would imagine some area over here, dA, I have all these charges passing through my area dA. So the total charge that passes through my area dA will be nothing but, let's say, the density of the electrons of my system. Well, if I have a denser system, there will be more charges passing through my area. It will be proportional to the velocity of the electrons, the charge of the electrons, and remember the charge of the electrons is minus E, and times the area element. So this will be the charge passing through this very small area, dA. Now this combination is what we call, well, this combination is in fact the charge passing per unit time, by the way. This is dq by dt. The charge passing per unit time through a given area dA. This is what we call the current density. It's a vector. So the current density itself is a vector. It has a direction and it has a magnitude. Well, usually we don't care about the current densities. We have these very thin wires in our circuits, and we would rather find how much total charge passes through my wire. So then what we do is we just integrate the current density over a cross-sectional area of my wire. This is what we call the current. Now, since we are taking a cross-sectional area, this is integrated over the cross-sectional area. The current itself still has some direction information. So if this is your area, the current can be flowing in this direction or in the opposite direction. So it has two directions. Nevertheless, it doesn't carry as much direction information as a vector. So it's not really a vector, it's just a number. It's just like the flux. Remember, the flux can be both positive and negative. Nevertheless, it's just a number. The current is also just a number, it's not a vector. It can be related with a vector itself, but the current is not a vector. So we have this current, and we know that the current is proportional to the current density inside, and the current density is proportional to the drift velocity, which is proportional to the electric field inside. So it is the current, the total current we have that is running across our wire is proportional to the electric field. And if we have an electric field, we basically have some potential difference between these two ends. So I have, well, let's see. This was our conductor. We connected it to a battery. So there's some current running through the battery. We know that the current is proportional to the electric field inside, which is proportional to the potential difference across the battery or across these two systems. The current is proportional to V, and we define this proportionality constant to be 1 over R. R is what we call the resistance. The smaller the resistance, the larger the current we have. Well, in a sense, you can just think of this as the mass. Mass is resistance to motion, and resistance of a circuit element is the resistance to a potential difference. So if you have a fixed potential difference, a system that has a larger resistance will create a smaller current. A system that has a small resistance will create a larger current. It's analogous to the mass in mechanics. So how is it related? How is this resistance related with the properties of the material we have, the size of the material we have? You see, here we had already defined the current density. And we also know that the drift velocity itself is proportional to the electric field. And so this whole thing is proportional to the electric field. Proportional to, and the proportionality constant is what we call the conductivity. So what does the conductivity depend on? Well, the density of your charge carriers, in this case we have the electrons that are moving, that are carrying the current. The density of the electrons, the drift velocity that can be created by the given electric field, it will depend on the local. Well, the important thing is that here we have the local properties. It doesn't depend on the shape of the material, for example. The shape doesn't enter into this relation. So this is a property of the material itself, just like its mass, its volume. Now we have another property, so-called the conductivity. Now if this is the electric field, this is the current density, and let's just assume that it is homogeneous everywhere. So the current will be J times A. Area is the area of our material. So I have this material, I'm imagining this material. It has a cross-sectional area A. Let's say it has a length D. And then I have some uniform current density running through it. So the total current is nothing but the current density times the area, which is sigma times the area times the electric field inside my material. But electric field is nothing but the potential difference across the two ends of my material. So I'm just assuming I connect this into V. I'm just assuming, I'm making lots and lots of simplifications. I'm assuming the electric field is uniform so that I have a uniform material. Furthermore, the current is distributed uniformly. Those are my assumptions. Under these assumptions, the total current is related to the applied potential through this relation. And this relation I can also write as, remember this was defined as V over R, so R is nothing but 1 over sigma D over A. And again, this 1 over sigma also appears quite often, so that it is also given a name. We define 1 over sigma as rho. This is called the resistivity. This minus. I have electrons. Minus E, Coulomb. The charge of an electron. This minus E is the charge of the electron, sorry, if I didn't mention it before. I mean, just remember the parallel plate capacitor. I mean, we are just thinking of this whole system as if it's a parallel plate capacitor. And we know that the potential difference across the plates of a parallel plate capacitor is just E times D. Also, we have already said that the electric field is the derivative of the potential. So this is the change in the potential divided by the distance over which I have that change. Again, this rho, the resistivity, is a property of the material itself. Now, of course, you can imagine much more complicated shapes, like rather than having a cylinder or a rectangular prism, you can imagine, I don't know, a pyramidal shape, or you can imagine, I don't know, a spherical thing. But nevertheless, the basic idea is the same. What is the electric field that you are creating by applying a potential difference? So you have to first exert a potential difference, identify what your electric field is inside your material that would create that potential difference. Once you identify the electric field, you can determine the current density using this conductivity. Once you have the current density, you can find the total current. In principle, everything is well defined for an object of an arbitrary shape. It's in principle. Well, if you want to put it in practice, it gets really complicated, so we stick with such simple shapes. If you want to find the resistance of a complicated shaped object from a complicated material, you just go and measure it. What is the unit of J? Well, let's see. The I, J, dq by dt was defined as J dot dA. So the unit of J is coulombs per second meter squared. So it is the charges that passes through a unit area per second, per unit time. That's what we call the current density. Now the resistance, we also define it as ohms. This is just a definition. And if you also note that we have this relation, I has the units, the charge that passes through our wire per second, this is coulombs per second. The resistance, it can also be written as V over I. The unit of V is volts per coulombs per second. Volt second per coulomb. Now, coulombs per second, we also define it as ampere. The unit is just A. Questions? Okay, so let's see. Is capacitors a kind of a resistance? What is the resistance of a capacitor? No, there's one question. Let's answer that question first. What is the resistance of a capacitor? Infinite. I mean, when you reach stationary state, that is, nothing is changing anymore in your system, when you connect a capacitor to a battery, it has infinite resistance. Because when everything comes to stationary state, there is no current passing through the capacitor. The charges are fixed, they cannot move anymore. So let's see, this, if we stick with this definition, this is J is coulombs meters per second. The unit of NE is numbers per volume divided by meter cube. So it is coulombs per second meter squared. Remember, this number density tells you how many electrons you have in a unit volume. So its unit is numbers per meter squared, meters cube. So also from this definition, you get the same unit. No, it does have. I mean, it's numbers per meter cube. Other questions? Now, by the way, the capacitor, you can think of a capacitor, at least for a short amount of time, more like a battery itself. It creates a potential difference. But of course, that potential difference, as the charges get lower, gets low, starts to go to zero. So this is the question, if I understood it correctly. Let's just imagine we have this wire over here, and electrons are moving in one direction. There's a current running through it. And then we have another wire, there's another current running through it. Which? Okay. Okay, it's the electric field inside the wire. No, electrons are not carrying a photon with them. Hmm? No, electrons are not carrying photons. No. I mean, electrons are moving from, let's say, up to down. The photons are moving towards me so that I can see the light. Okay. Okay. They do, but not the photons. Yes. What's an electric shock? I mean, when are you shocked by an electron? I mean, when are you electrocuted? Well, like whenever a current runs through your body, that's what we call the electric shock. Now, if you would go and touch a high voltage cable that you see, you will feel an electric shock. But then you see all those birds sitting on the wire. Why aren't they electrocuted? Well, I mean, if it just enters your body and leaves your body from some other point, you will be electrocuted. You see, what does the birds do? This is the wire. Okay. So this is the ground. This is where you are standing. Okay, if you would just hold the wire, then you will be electrocuted. Okay, so this is something you shouldn't do. But then you see all these birds. Okay, some kind of a bird standing over there. They are not electrocuted. How come? They're not. I mean, you see, in your case, the current will run through your body to the ground. So there will be a significant amount of current that's running through your body. That is what causes you to be electrocuted. But in the case of the bird, I mean, if we would just look very close to this point, this is the wire, and we have the birds sitting over there. This is the other leg. Okay, so I mean, you see, this is a really good conductor. Mainly, most of the time, they are made of very good conductors. So there is some huge amount of current running through it. Well, in fact, a small current is running through it. I. And the potential difference between these 2 points is I times R. R is very small. So there is not much a potential difference between these 2 points. Furthermore, the resistance of the bird, if the current would go around this circuit, is huge. So V is small, R is huge, there is a very small amount of current running through the bird. In your case, the relevant potential difference is the potential of this point and the ground. That's like 10,000 volts. There's a huge potential difference between your hand and your feet. So that's what causes you to be electrocuted if you hold the wire. I mean, if you are not touching the ground, I still would advise you against holding with both of your hands. Hold with one hand, and then you will not be electrocuted. And if there is a thunder strike on the ground, don't keep your feet open. If there is a thunderstorm, for example, let's say there is a thunderstorm, there are all these clouds. There is a thunder strike. Keep your feet closed. Do not open them. Because although the ground is a conductor, it still has a significant resistance. So if you open your legs wide, there will be a significant potential difference between those 2 points. If there is a large potential difference between those 2 points, then a significant portion of the current can run through your body, which is not something you would like to have. If you keep your legs closed, there won't be such a huge potential difference. Try various methods and report back to us your observations. Okay? Okay, any last questions? Yes. Well, you see, this is the point A, this is the point B. The potential difference between A and B will be the current running through the wire times the resistance of the wire. That part only. But resistance of the wire, now, resistance of the wire, if it's made of copper, it will be very small. The resistivity is very small. Since the resistance of the wire is very small, the potential difference between A and B is very small. If the potential difference between A and B is very small, the potential difference between A and B will also be equal to the current that runs through the bird times the resistance of the bird. So the current that runs through the bird will be equal to the current running through the wire times the resistance of the wire divided by the resistance of the bird. Now we will see that already the current running through the wire is not that huge. It is at a very high potential, but at a very small current. And the resistance of the wire compared to the resistance of the bird is negligible. So this is small, this is much, much smaller than 1. So the current that runs through the bird will be negligible. Other questions? Yes. Well, in the case of this kind of current, when the current is running all in the same direction, there is no difference. Okay, see you on Thursday.